cosmologists have fostered a leave plan, utilizing our new $10 billion toy. It will be a long time before that venture turns into a reality, and assuming that it goes as planned, the excursion to Proxima B will require around 20 years. Practically, it will be quite a few years before we can confirm if there is, for sure, life on that planet. The deep-rooted question remains: are we genuinely alone in this universe? The James Webb Space Telescope has found some intriguing things a long ways off from Earth, bringing us closer to a potential answer. Our quest for life beyond us has been relentless throughout every human development, leading to great numbers of media writings and hypotheses regarding this matter. Our wonder about our place and isolation in the universe has been consistent, ingrained in us to continuously seek a companion. Regardless of how alien-like we may be, we are drawing nearer to the answers we need. But are they the answers we are searching for, or are they significantly more frightening? Join us as we explore the most recent revelations in the realms of galaxies and planets on the journey to find something we might not be ready to observe. Researchers have found what could be the most pivotal disclosure in history. Back in 2021, when the James Webb Space Telescope was planned to launch, a fascinating theoretical inquiry was raised about the capabilities of our technology. Might our telescopes detect artificial light on another planet? Proxima B, the nearest exoplanet to Earth, is in the habitable zone of our closest neighbor, the small star Proxima Centauri, around 4.25 light-years away. Since the exoplanet is multiple times closer to its star than Earth is to the Sun, Proxima B was thought to be perfectly locked with an extremely permanent dayside and nightside. This is similar to our Moon, which always faces Earth with the same side. A speculative mechanical civilization on Proxima B could move heat and power from the dayside to the nightside using photovoltaic cells. In a paper with M.V. Lingam as one of the analysts, it was shown that significant illumination of the dayside by solar chargers could be detected with future telescopes. Since the James Webb Space Telescope, JWST, is further developed, it would permit us to expand our search for artificial lights to tenable exoplanets like Proxima B. Now, in 2024, the JWST could have found the lights we were searching for, potentially propelling us into another large wave of human advancement. But first, let us delve into the universe of planets and exoplanets to figure out how this was possible. James Webb's mission explores Proxima B's mysteries. Since forever ago, people have pondered the idea of the universe posing normal yet incredibly troublesome inquiries. What are we? Where do we come from? And where do we go? Now, in the era of dramatic, innovative progression, one could contemplate whether we are any nearer to answering these inquiries. Pose this to a rationalist, and they might say we are currently at level 0 of understanding ourselves in the universe. Ask a space expert and watch them bounce around in fervor as they hurry to enlighten you about the most recent revelations regarding the universe, utilizing their clever tools. Albeit not given much attention by the general public, these are clearly a sign of human development itself. We now have the world readily available, and it is time we push forward and get the universe readily available too. One such method for doing that has been derived by researchers and cosmologists through the technology we harness. A particular product of that technology is now responsible for the new revelation of what may be light on another planet, light-years away. Yes, we're discussing the James Webb Space Telescope. The James Webb Space Telescope is the creation conceived out of the traditions of human campaigns into space to address some ever-present questions. Are we alone? Who is out there? Where do we start? And where do we end? This infrared stargazing apparatus has already begun addressing these inquiries, albeit to some degree. First, you might ask what Proxima B is. Proxima B, sometimes referred to as Alpha Centauri CB, is a super-Earth exoplanet that orbits an M-type star. Super-Earths and M-type stars may sound confusing, but don't worry. This text will clear up your burning questions. Super-Earths are a class of planets that are more enormous than Earth but lighter than ice giants like Neptune and Uranus. They are truly one of a kind, and they can be composed of gas, rock, or even a mix of both. Their sizes can vary from twice the size of Earth to multiple times its mass. They truly put the super in super-Earth. Regarding Proxima B, it is a super-Earth and an exoplanet, meaning it orbits outside the solar system. The very first possible evidence of an exoplanet was observed in 1917, though it managed to stir up little interest and acceptance. However, in 1992, the first confirmed detection happened, leaving researchers astounded. Another exoplanet identified in 1988 was confirmed in 2003. As of April 1, 2024, there are 5,653 confirmed exoplanets in 4,161 planetary systems, with 8,196 systems having more than one planet. These glorious discoveries are orbiting an M-type star. To understand the M-type star, you need to know about the red dwarf. A red dwarf is the smallest type of star in the main sequence, hence the name. In the neighboring regions of the Sun, red dwarfs are by far the most common kind of star to be found in the Milky Way. They have very low luminosity, making them not that easy to observe. These elusive stars have variable definitions and names depending on their temperatures and sizes. For instance, M-dwarfs or M-type main sequence stars yield a maximum temperature of 3,900 K, hence their name and characteristics. Returning to Proxima B, its mass is known to be equivalent to 1.07 Earths. Strangely, it only takes 11.2 days to complete one orbit around its star, compared to our 365.25 days. You can gauge the size of the star Proxima B is orbiting by measuring the entire electromagnetic spectrum. The star has a total luminosity of just around 16% that of the Sun. Moreover, in the visible light spectrum, its luminosity appears even dimmer, as it only emits 0.56% of the Sun's luminosity. More than 85% of its emitted energy is in the infrared radiation range. Orbiting around 5 cents away from its star, Proxima B's discovery was reported in 2016. You may be asking, why Proxima B? With so many stars, planets, and systems, why are we so focused on this particular celestial body? There are several reasons that add to astronomers' strong fascination. Above all, Proxima B is the closest known star to our Sun and, by definition, is relatively nearby. Although 4.2 light-years is a significant distance for us Earthlings, in the grand scheme of the universe, it is a mere blip. Hence, Proxima B, our nearest known star, is high on the priority list. It is also part of the triple star system called Alpha Centauri. Despite Proxima B's low luminosity, the system itself appears as one of the brightest star clusters in the night sky, just behind Sirius and Canopus. However, the most intriguing aspect of Proxima Centauri B is that it could potentially be habitable, since it falls within the habitable zone. The possibilities surrounding the star are endless, prompting cosmologists to explore its depths and potential. This is where the James Webb Space Telescope comes in. The 4 critical objectives of the JWST are to look for light from the first stars and galaxies that formed in the universe after the Big Bang, focus on universe formation and evolution, understand star and planet formation, and review planetary systems and the origins of life. As the JWST continues its investigation of the said exoplanet, we draw closer to the fulfillment of these missions, from searching for extraterrestrial intelligence to exploring exoplanets. So what exactly is SETI, one might ask? Considering that people have always been curious, it makes sense that a mission like SETI appeared. Imagine that the cosmos is a grand cosmic expedition but with a twist. Instead of gold, we are tasked with keeping watch for signals, specifically electromagnetic whispers, from civilizations beyond our wildest imagination. SETI stands for the search for extraterrestrial intelligence, our collective effort to detect signs of intelligent life lurking amid the stars. Our curiosity endures, does it not? Shortly after radio technology came into use, visionaries like Nikola Tesla and Guglielmo Marconi dreamed of using these devices to contact the stars. Tesla even liked the idea of communicating with Martians using his wireless transmission system. Fast forward to the 1960s, and we find ourselves amidst Project Ozma, the brainchild of astronomer Frank Drake. Armed with a robust radio telescope and curiosity, Drake scanned cosmic radio transmissions for signs of something beneath the surface but came up with little. The search continued with researchers around the world tuning their antennas to the cosmic symphony. In the Soviet Union, scientists also sought signals from the stars, led by the famous ISF scholar. The stage was set for an astronomical standoff when a mysterious transmission named the WOW signal cut through the cosmic noise, bringing excitement to mainstream scientists. As the years passed, the search for cosmic partners intensified. As our quest for knowledge about the universe progresses, the search for extraterrestrial life remains one of the most captivating and profound scientific endeavors. The idea that we are not alone in the cosmos resonates deeply with both scientists and the public alike. The vastness of space and the sheer number of stars and planets make this quest both daunting and exhilarating. Astronomers have long speculated about the possibility of life elsewhere in the universe. The discovery of extremophiles, organisms that thrive in extreme environments on Earth, has expanded our understanding of where life could potentially exist. These microorganisms live in conditions previously thought to be inhospitable, such as deep-sea hydrothermal vents, acidic lakes, and arid deserts. This discovery suggests that life might be able to exist in a variety of environments beyond Earth, potentially increasing the likelihood of finding extraterrestrial life. One of the major areas of research in the search for extraterrestrial intelligence, SETI, is the study of exoplanets. Exoplanets, or planets outside our solar system, are prime candidates in the search for life because they may have conditions similar to Earth. Scientists use various methods to detect these distant worlds, including the transit method and the radial velocity method. The transit method involves observing the dimming of a star's light as a planet passes in front of it, while the radial velocity method detects the gravitational influence of a planet on its host star. Recent advancements in technology have significantly enhanced our ability to detect and study exoplanets. The launch of the Transiting Exoplanet Survey Satellite, TESS, has furthered this effort by surveying a wide range of stars to identify potential exoplanets. TESS aims to find exoplanets that are closer and brighter than those discovered by previous missions, making them ideal candidates for further study. Another innovative approach involves direct imaging of exoplanets. This technique uses specialized instruments to block out the light from a star, allowing astronomers to capture images of the planets orbiting it. Direct imaging provides valuable information about the planet's atmosphere and potential habitability. For example, the upcoming Extremely Large Telescope, ELT, and the Nancy Grace Roman Space Telescope are expected to significantly advance our capabilities in this area. The study of atmospheres is particularly important when assessing the habitability of exoplanets. The composition of an exoplanet's atmosphere can reveal crucial information about its climate and potential for supporting life. For instance, the presence of oxygen and methane in an atmosphere could indicate biological processes similar to those on Earth. Upcoming missions such as the James Webb Space Telescope, JWST, are equipped with advanced spectrographs that can analyze the light passing through an exoplanet's atmosphere, providing insights into its chemical composition. In addition to studying exoplanets, researchers are also exploring the possibility of detecting signals from advanced extraterrestrial civilizations. The idea of using radio telescopes to listen for signals from other civilizations was popularized by projects like SETI. However, recent advancements have expanded the search to include other types of electromagnetic signals and even optical communications. One notable example is the Breakthrough Listen initiative, which aims to scan the entire sky for radio signals and optical laser transmissions that could be indicative of extraterrestrial intelligence. This initiative uses some of the world's most powerful radio telescopes, such as the Green Bank Telescope and the Parkes Telescope, to search for signals across a wide range of frequencies. The initiative also includes efforts to search for narrow-bandwidth optical signals, which could potentially be used by advanced civilizations to communicate across interstellar distances. In addition to radio and optical signals, researchers are also exploring the possibility of detecting signs of extraterrestrial technology through other means. For example, the concept of Dyson spheres, hypothetical megastructures built around a star to capture its energy, could potentially be detectable through infrared observations. The JWST's ability to observe infrared light makes it well-suited for this type of search. The search for extraterrestrial life also extends beyond the detection of signals and the study of exoplanets. Robotic missions to other planets and moons in our solar system have provided valuable insights into the potential habitability of these celestial bodies. For instance, missions to Mars, such as the Mars rovers and orbiters, have explored the planet's surface and atmosphere, searching for signs of past or present life. The discovery of seasonal changes in methane levels on Mars has raised intriguing questions about the possibility of microbial life. Similarly, missions to the icy moons of Jupiter and Saturn, such as Europa Clipper and the upcoming Europa Lander, aim to explore the subsurface oceans beneath their icy crusts. These oceans may harbor conditions conducive to life, and understanding their composition and dynamics is crucial in assessing their potential for habitability. As we continue to push the boundaries of space exploration and technology, the quest for extraterrestrial life remains a central focus. The collaboration of international space agencies, research institutions, and private companies is driving progress in this field. The development of new technologies, such as advanced telescopes and space probes, enhances our ability to explore and understand the universe. In addition to technological advancements, the search for extraterrestrial life also involves philosophical and ethical considerations. The discovery of extraterrestrial life would have profound implications for our understanding of our place in the universe and our relationship with other potential intelligent beings. It would also raise questions about how to communicate with and interact with such beings if they exist. Overall, the search for extraterrestrial life is a multifaceted and dynamic field of research that encompasses a wide range of scientific disciplines and technological approaches. As we continue to explore the cosmos, the potential for discovering new forms of life and understanding the nature of our universe remains one of the most exciting and profound aspects of modern science. The journey to uncover the mysteries of the universe is far from over, and each new discovery brings us one step closer to answering the age-old question: are we alone in the universe?